particular problem, we have a beaker that has a weight of 2 newtons, not kilogram, so it gives us the weight already in units of newton. And this is filled with 5.0 times 10 to the negative 3 meters cube of water. So meters cube here would imply this is the volume of water that's filled up. And this is a rubber ball weighing 3 newton. Once again, the weight of the ball is given, not the mass. It's entirely under the water. And it says here it is tied to a string that's hooked to the bottom of the beaker. And it says the tension in the string is 4 newtons. And it says the water fills the beaker to a depth of 0.2 meters. Okay, and it gives the density of water, and it does ignore atmospheric pressure effect. All right, so we need to pause A, B, C, D, and E. And here's the diagram on the bottom. Let's go and crack this out. Part A wants us to find the weight of the entire apparatus. So in this case, the apparatus includes the beaker itself, the weight of the water, and the ball. Okay, so in order to do so, to find the total weight, you would just find the weight of the beaker added to the weight of the ball plus the weight of the water. So the weight of the beaker is already given as 2 newtons. So here I do want to point out weighing 2 newtons. So this is just the magnitude. If you want to get technical, weigh is a vector which points downward. But I notice here it just gives us how much the object weighs in terms of just the magnitude. Okay, so it doesn't have the negative sign, which is okay with me. All right, so here I replace the weight of the beaker with just a positive 2, just the magnitude. It also tells us the weight of the ball, which is 3 newton. Once again, just the magnitude of the weight. So there's 3. And then, well, we need to find the weight of the water. Okay, well, but to find the weight of the water, by definition, weight is mass times acceleration due to gravity at the surface of the planet. So all I did was I broke weight into its definition. Weight is mass times gravity. What mass? In this case, we're trying to find the weight of the water, so we need to find the mass of the water. We already know G is 9.8. Okay, so once again, all we have to do is really find M water. So to find the mass of the water, all I can do is use density is equal to mass over volume. Why would I do this? Density of water is a constant 1,000 kilograms per every meters cube. So we know the volume already. We know the density. The volume was given in the early statement. If you were listening, it was 5.0 times 10 to the negative 3 meters cube, right? Meters cube implied that's the volume of the water that's been poured into the beaker. So the only thing we don't know here is the mass, but to find mass, all we have to do is algebraically isolate for M by multiplying both sides by the volume of the water that's in the beaker. So I want to go ahead and do that, multiply both sides by V. So therefore, to find mass, I know density, I know volume, so I'm just going to do a little plug and chug. Density is given as 1,000 kilograms per meters cube. The volume of water here is 5.0 times 10 to the negative 3 meters cube, as stated in the wording. And if you simplify this on your calculator, you get a value of 5 kilograms. Well, now that we know there's 5 kilograms of water in the beaker, we can just substitute that in. So here's mass. Mass is 5 kilogram. At this point, I do want to point out G here is 9.8 and non-negative because I'm just trying to find the magnitude. Okay. So everything else is just given in terms of magnitude, 2, 3 newtons. So I'm just going to find the magnitude. So if you simplify all of this, you'll get 54 newtons. However, on a technicality, weight is a vector. It's like the force of gravity, and the force of gravity has a direction. It didn't say anything about the magnitude, so I'm just going to include the negative sign, but it's up to your professor and your instructor. 54 newtons would probably be sufficient because everything else is given in terms of magnitude, so I'm assuming they want magnitude. But I'll just put the negative sign there just for proper notation. Okay. All right, let's do B. B says on the dot, draw and label the forces, not components that acts on the ball. So here's a little dot. Well, here's the ball itself in white here in the beaker. Well, to draw the free body diagram, all you have to do is identify all the forces acting on this particular ball inside the water, underneath the surface of the water. Okay, so, excuse me. Let's do part B. Excuse me. I thought I have it on the same side, but apparently not. I have it on this side. All right, so to find the forces, I'm just going to identify this. This is my tension. Tension is going to point downward in this problem because it's pointing towards the pivot where it's being tied to. So the problem says that it is attached to the bottom of the beaker. So tension in this case will be pointing downward. And then here is the weight of the ball itself, okay, or F of G, if you want to call it that, or you can just call it W. It doesn't really matter. So I have 2 forces pointing down. And then there's the force of buoyancy because this is in the suspended in the liquid. So the force of buoyancy is always going to point up. And here I drew F of B, a little longer. Again, these vectors are not drawn to scale. I know it's longer because, this ball staying still and you have 2 forces pointing downward. So the one force pointing upward has to equal to the magnitude of these 2 arrows. So out of good habits, I would definitely suggest drawing this F of B for this diagram longer, just so you can show people that you know that there are two forces acting against it, and the sum of these two negative forces equals to the magnitude of the one pointing upward. Okay, so I'm just going to transfer that into my free body diagram here. So it says it wants where the dot is, so I'm just going to go ahead and call T f of g, and then last but not least, there's f of b. So in this case, f of b equals to the two forces pointing down, which makes sense. The object's at rest. All right. Part C asks you to calculate the buoyancy force. Okay. So therefore, to calculate the f of b here, I'm just going to set up Newton's second law of motion. However, this thing is not moving, so therefore I can just go ahead and expand this. Well, what are the net forces? I'm just going to do positive minus negative. Okay, so I'm going to do up minus down. So the negative sign's already been taken care of for you. Or you can add a negative if you want. So I'm just going to say f of b is positive minus f of t, which is pointing down, minus f of g, which is pointing down. That equals to ma, but a is 0. So from here to isolate for f of b, I can move the negative t and the negative f of g to the right side, which makes both them positive, which makes sense, right? In the free body diagram, it states that f of b is the one force pointing upward, but the system stays in equilibrium, so therefore it must equal to the magnitude of these two vectors pointing downward, which is the center of this statement here, right? You're saying f of b pointing up equals to the two pointing down, just magnitude, because the negative sign has already been taken care of for you. All right. And that the wording says here the tension is 4 newtons, and then it also says the weight of the ball, once again, is 3 newtons. So we know T, we know F of G. T is 4 newtons. The weight of the ball is 3 newtons. Once again, these are just magnitude. So we can say that F of B has a magnitude of 7 newtons, but it didn't say just the magnitude. So once again, to be proper, I want to put the plus sign there because for this problem, F of B points up. So if your instructor doesn't really care, you can just say 7 newtons. Okay. All right. That is the answer for C. So not bad. D. D, I think it's the hardest one out of them all. It says calculate the pressure due to the liquid. Calculate the pressure due to the liquid, aka the pressure, the gauge pressure here at the bottom of the beaker. So to do this one, you have to know the function for gauge pressure. Gauge pressure is simply rho GH. Gauge pressure depends on height only and nothing else. Okay. So here, the density of water is given, right? That's 1,000. G here, I'm just going to go ahead and use 9.8 because we're just, pressure is the scalar value, so it doesn't really matter if you put a negative. Just know that pressure is the scalar, so if you get a negative, just give the magnitude. So here's rho, once again, it's 1,000. G is 9.8. And the height of the water here in this particular diagram is 0.2. So if you plug all that in, you'll get that, right? So the work is easy as long as you know your gauge pressure function and you know what that it depends on height. This becomes pretty straightforward. All right, and then last but not least, part E, a conceptual part here. It says the string is cut and the ball rises to the surface and floats. It says indicate whether the water level is higher, lower, or the same after equilibrium is reached. Well, this one I think is an intuitive thing and a common sense thing. So I'm gonna go with lower because here when the ball is in the middle, right, it takes up a certain amount of volume, right, of the water. So if you can visualize it, once this ball starts floating up, there's less volume of the ball displacing the water, right? So as you push the ball down, once the whole entire ball's inside the water, it occupies its volume, causing the volume to move upward because that volume has to, occupy space. Okay, so but once the ball moves upward, then the water level would have to drop. Okay, so I would go lower because of that. Okay, now here's a visual diagram for you, just in case you have no experience with this kind of stuff. So here in this diagram, this is the best diagram I can find for you. So let's say here if you have a ball and you push it downward, as you can see, it causes the water level in the beaker or whatever container it is to rise. And if you don't believe me, just try it yourself. Okay. However, once you let the ball rise to go back upward, you can see here the difference in two levels. Here, the water level is high because the volume of the ball is causing a sort of liquid displacement here. But once that ball rises, that volume no longer causes the displacement, so the water level drops back down. So I would say this is your initial quote-unquote water level if the ball is submerged in the water. However, if the ball is let loose and it rises again, therefore the water level has to drop. So here's your starting water line, here's your final. So as you can see, it dropped and it didn't go up. All right, and that's it. I hope this helps. Stay nerdy, don't be whack.